So I'm going to focus on just periodic comets rather than the vast multitude. And what I'm going to be telling you is really the results of the visual and electronic observations over many apparitions that tell us a little bit about what's going on a comet. So there are a huge variety of comet orbits, and there's a huge variety of comets themselves in those orbits. And the first one that we got a glimpse of was Comet Halley, and that generated some of the models of comets where you got a nucleus, a amalgam of blocks surrounding it, the features of the coma and the tail and so on. I think what we didn't realise from the first few spacecraft passes is the vast diversity in shapes, and these became clearer as more and more comets were imaged from close up, showing a wide variety of shapes and also a wide variety of makeup of the surface. We can start seeing geology, if you like, of what's going on. And we gradually got closer and closer, more detailed. These are clearly quite rocky objects with some ice rather than icy objects with some rock. We managed to hit one, briefly creating an increase in brightness, but only very briefly. So even something that from the spacecraft looks an incredible change, from the ground was barely detectable. And then the fragmenting process, boulders coming off, but also that the activity is not uniform across the comet's nucleus. And then, as Nick says, most recently Churyumov-Gerasimenko, with the fantastic resolution that we've seen, showing layering, geological processes in action, where we've got these cliffs and the debris below them, and even objects like sinkholes, which we can see on Earth, but this is a very different type of sinkhole. So from space we get that variety of comets. We know that there's a variety of cometary orbits, and one of the things that I hoped to say but never quite had the time to do the analysis was that does the shape of the orbit influence the behaviour of the comet in the long term. So there's going to be lots of items where the research is in the future rather than in the present. And the section doesn't really have observations going quite as far back as the BAA tapestry.
They didn't conform to the file naming convention.
They certainly didn't conform to that, or the ICQ format for the visual observations. However, the comet has been well observed in the past, and in principle I should be able to go back and get visual equivalent magnitudes or absolute magnitudes for each of the returns. Obviously I have strong links to Halley's comet because Halley station in the Antarctic is one of the ones that I've been quite heavily involved with during my career, but also my career took me down to the Antarctic to see Halley's comet from the continent for the first time of anybody. So that's quite a nice tick. So for this comet in the section archives, we only have one return, and you can't deduce much from a single return. But going on to the second numbered comet, we've got quite a lot of observations of that. And in this talk I'm going to give one or two illustrations, and people sometimes quiz me when I submit my reports on the comets of each year, why I haven't included more of the thousands of images that Dennis has mentioned. And one reason for that is I'm trying to aim at the broader BAA interests, and many of these images are for astrometric purposes and just show a little tiny splodge in the middle of a starry field, which for many amateur astronomers has very little interest. So I try and portray the comets that at least show a decent coma, perhaps have a galaxy in the background, or have a nice tail, or are in some other ways attractive to look at. in the hope that if people look at the picture, they might read the rest of the article as well. So, because there are so many returns for this comet, it's possible to lay them on top of each other in 20-year blocks, and quite remarkably, there's pretty good agreements between the various returns. And when we look at the absolute magnitude, that's the magnitude that the comet would have if it's a fixed distance from the Earth and the Sun, there's really no change that's significant going back to 1920. And this is a comet that people thought was in the process of slowly fading away and disappearing. So our observations show that actually there isn't much change. In this talk I'm just going to concentrate on the lower numbered periodic comets, and again we've got quite a lot of them. So this one's Comet 4P Faye, here showing a small tail as imaged by Dennis, and again we've got a lot of observations going back quite a good number of years in the archives. Putting them all on top of each other, there's quite a bit of scatter, but broadly speaking, when you get to the absolute magnitude, there's no significant change over the period when we've got reasonably good observations. So there's at least two comets that don't seem to be changing with time. The next on the list is 9P Temple. This is one of the ones that's been imaged from close up. Here there may be some drifts, but the data so far is a bit too scattered to be confident whether there's any long-term change in the comet's behaviour. Its sister comet that was discovered more or less at the same time but numbered a little bit later has a dramatically different sort of light curve. It's highly asymmetric, so that the comet brightens and is generally speaking brightest a little bit after perihelion and then fades much more slowly than it brightens. And this is what I describe as a linear type of light curve. And interestingly, for this one, if we plot the absolute magnitude against perihelion distance, we find a fairly good correlation. Some comets, because they go close to Jupiter, have their perihelion distance changed from one return to the next. And whilst in theory that should not have an effect on the absolute magnitude, the evidence is becoming quite clear that it does have a significant effect on how bright a comet becomes at each return. And by and large, comets are brighter if they're closer. In this particular case, the real difference is how the delay corresponds to the perihelion distance. And that's rather harder to explain. So how many days after the comet is closest to the Sun is it brightest? Clearly it will be interesting to see future returns to see whether this trend actually holds up or whether it changes. And what's this change caused by? Is it purely the distance from the Sun, or perhaps is it a difference in precession as the comet rotates? Increasing our numbering, we're now on Comet 15P. This is a comet that is intrinsically quite faint, and so it's not so well observed by the visual observers, and indeed even by the CCD and electronic observers, so a good target for future observations so that we can extend this range into the future. Some scatter in the results, but certainly the 2002 return seems to have been substantially fainter than these two. So 2008, 2014 quite bright, 2002 and 1960 relatively faint. And the problem is when you do the reduction, the perihelion distance hasn't really changed very much, although there is a correlation. On the other hand, these dotted lines tell you what the error bars are. And so you can pretty much really draw any line that you like and be reasonably confident that you're fitting something reasonably well. And unfortunately, the reason that these lines are so far away is that the perihelion distance hasn't changed a great deal for this comet. So we could do with a big kick from Jupiter to make it significantly different, and then we'll see a little bit more about what's going on. So 16P Brooks, this is another comet that never gets particularly bright, as perhaps can be told from this image, where it needs an arrow to point out even where the comet is in the field of view. So here there's certainly something anomalous going on with the 1994 observations, in that these ones are really much fainter than is indicated by the rest of them. But it has had quite substantial shifts in its perihelion distance, so this is a good target for seeing what change will occur in the future. So this year it's fairly close to Jupiter, so that its next return, if all you electronic imagers can make use of Nick's software, and more importantly still, send me the observations, and that's the key bit where it always seems to break down. We've got one person who's really good at observing lots of comets and sending me the observations, another person who sends me a few, and there are an awful lot of images out there which have never been reduced and the details sent to me to incorporate in the analyses. And if you don't do your reductions, the images are less useful than if you do the reductions. So moving out a bit, this is a comet that some returns it does quite well, others, because of the geometry, it doesn't put in much of an appearance. So it's due back next year, when it will come quite close to the Earth, and potentially there's a chance it could become a naked eye object if you're in dark skies. But again, this is a comet where the observations pretty much line up on top of each other. There's no obvious trend, but because it's quite a diffuse object and comes quite close to the Earth, it exhibits what's called a delta effect. Now in theory, if you correct for the distance from the Earth, that should be fine, but the human eye in particular tends to do strange things when you have large diffuse objects, and it becomes quite difficult to estimate exactly how bright it is. So this particular comet, because it's going to be large, the electronic analysis is not going to work terribly well, because we've generally found that the bigger and more diffuse comets really don't analyse terribly well. And equally, it may be quite difficult to get good visual magnitudes. But do your best, and we'll see how it all ties together as the results come in. Another comet that again sometimes puts on a good display and sometimes doesn't, because it comes quite close to the Earth's orbit. The observations at first glance really look quite well scattered, but we've got enough of them that we can subdivide into 20-year groups again, which is quite good. And then when we take the individual results, there's no great evidence for any long-term change in behaviour. So for many comets, what we're seeing is no net change. You might think, well, why bother? And that's because comets, as Richard I think is going to be telling us, do undergo catastrophic events, and that might change their long-term behaviour. So this is one that Nick has mentioned. It's done a recent close approach to us. there's very clear evidence for outbursts. So we can see a spike in 2001 and this one in 1995. And there was a hope that it might do an outburst this time round, but unfortunately it hasn't obliged us so far. If it had done, we would have had a really quite spectacular naked eye object. Because of those outbursts, it's very difficult to do a coherent analysis. Another of this year's close approaches, which produces really quite a good ion tail. Here's a more recent image by Gerald Rayman. It seems to behave itself quite well, more or less symmetric type of light curve. It does approach us quite closely, but for this comet the evidence for a delta effect is less clear cut than for the other one. So again, that means that we need further observations and research to try and disentangle why some comets seem to show a clear delta effect and others don't. Perhaps it's a spectral effect that the human eye responds differently to different colours. And then the famous comet that has been visited in detail, and before the spacecraft encountered it, I analysed all the observations, and one thing is very clear, that there is a change in brightness of this comet from return to return. It's really quite dramatic, and when you analyse that absolute magnitude, it seems to be getting brighter with time. There are other ways of portraying the same data, so we can look at what the perihelion distance is and how bright the comet is, and this does seem to show just about a significant trend with perihelion distance. And because we know this comet is highly asymmetric, we also know that it's precessing, we know that that rotational period is changing, it may be a combination of those factors that is creating this apparent trend in brightness of the absolute magnitude and also in respect of the perihelion distance. Now at the moment the perihelion distance, I think for the next return is somewhere out here, and therefore I can make a prediction that if this correlation is correct, we're going to have an absolute magnitude somewhere up here the next return. If that prediction is wrong, then this theory goes back to the drawing board and we can try again. But this is science because it's making predictions rather than using blind belief. And interesting, the professionals have done similar analyses, and what strikes me as being a bit inexplicable is this disconnect in the two graphs at perihelion. Now nature very rarely is discontinuous unless you have an outburst. There was no evidence, I believe, for an outburst at perihelion, so something in that curve fitting has gone wrong. Yes, it can be asymmetric, but the two bits really should link up if it's perihelion plays a large part in it. And of course we know that it's this rubber duck shape that's moving around in really quite a weird way, and it's perhaps not surprising that a comet with such a misshapen form is going to have quite a strange light curve. Also, there's loads of different geology on the surface, and so which of those areas are best illuminated by the sun is going to have an effect on the production of gases as well, hence going into the coma. Increasing our numbers, Comet G-class, quite a distant comet this one, and one that broadly speaking seems to be getting slightly fainter with time. So this is one that had a Jupiter encounter in 1981. the orbit's been pretty much constant since then, but here there is some evidence for a slow secular decline in brightness. 88P Howell has had several Jupiter encounters which have made changes to the orbit, and it's really quite difficult to explain why the light curves are different each time. There's a number of possible things. It could be that the active areas on the comet are changing. It could be that the comet's nucleus is precessing. This might be another of these misshapen objects. An outburst of some sort between 2004 and 2009, where the comet is now slowly regressing back to the mean curve. That's a possibility. So if it was a very distant outburst, we might not have noticed. Or it could be a delayed response to changes in perihelion distance that occurred again around about that time. So I'm afraid we need more observations of it, but one thing that appears to be the case is that the delay in the peak magnitude again is decreasing with time. So this is another one where that delay between perihelion and the time that the comet is brightest is slowly differing. And then finally, because I'm going to stop at number 100, and 96 is the last one that we have a whole sequence of observations of, 96P Mach-Holes. This is usually very difficult to observe from the ground. It goes in very close to the sun, and so from spacecraft, particularly the SOHO spacecraft, and I'm sure Alan will be mentioning this later, it can get very bright as it goes through the SOHO field. But broadly speaking, the brightness of the various returns has been consistent. So although it's going very close to the sun, you expect quite fierce erosion of the cometary nucleus. That doesn't seem to be playing out in the overall shape of the light curve. So much to Nick's surprise, I am going to hit the time, so I'm now on to the conclusions. So this is very much a work in progress. There's plenty more periodic comets that we have observations for in the archives, and they keep coming back, so there's no excuse for not going out and observing them at each return. It's very clear that there's a wide range in behaviour of these objects. No two comets are the same. Whether they're always like cats and doing what they want to is another matter, but so far the observations at least suggest some consistent patterns in behaviour from one return to the next. Your observations are valuable. Without them, we have no idea whether there's any change in behaviour from one return to the next. And that is quite important. By the time I've got a really good number of these reductions done, then we can draw much better conclusions. Do reduce your observations and submit them. That's really a vital take-home message, I hope, from today. And yes, we do need further observations. Now, if you have to concentrate on a particular type of comet, yes, do take those nice graphic images of the brighter objects, but if you've only got time to image so many comets, do concentrate on these periodic ones, because I think that will give us the greatest scientific return from the amateur observations. So just concluding with what you might go and look at over the next 12 months or so. From September onwards, we should be able to pick up 24P show mass, and then next year we've got 48P Johnson and 21P Giacobini-Zinner to image. And who knows, there might be a surprise comet, but I don't think it will be a periodic comet that gives us a surprise, unless it's one with a very long period that should come back. So,
Fantastic.
25 seconds to spare.